All right, guys, are you excited? Because I'm so excited because we're finally going to do some calculus. Yay! I know you're thinking, what? We haven't been doing calculus this whole time, but it's been so hard. No, actually, up until now, we've just been mostly reviewing things that you need to know for calculus and things that we learned in pre-calc. But really, this is calculus right here. This is the first topic of calculus. And I know that a lot of you guys actually looked at limits last year in pre-calc, which is so great because then this won't feel so hard, okay? But even if you didn't look at this in pre-calc, that's okay because it's not crazy. Anyway, so this is one of the first topics of real calculus, and the next one that this is going to lead into is derivatives. So they really do link to each other. All right, so what is a limit? Well, basically, a limit is a y value which a function approaches as x approaches some value, okay? So that might not make a whole lot of sense, but basically what we're saying is, remember when I say, what is the function doing at this point? What is the function doing at that point? Well, when I say the function, I mean the y value of that function, right? I mean the output, because the output, or the y value, is the function, okay? So when I say what is the limit of the function, I want you to think of the y value of that function. Okay, so first let's figure out how to write limits. So when you write a limit, you are going to write it just like you see it right here, okay? And only like you see it right here. You're not going to write limit x equals, no, you're not going to write it like that. You're not going to write just something like x goes to c, y goes to 5. Nope, that's not how you're going to write a limit either, okay? You're going to write the limit as x approaches some number of f of x equals some other number, okay? That's how we write limits. We always write them the limit, just lim, of x as x approaches c of f of x, or whatever function we're talking about, equals some number. This big L just basically means some number that's a y value, okay? So let's see what this actually means on the graph. So I have the limit as x approaches -4 of f of x. So basically what this is saying is if I am walking on this function, right, and I can't leave this function and I'm just walking on the function, when I get really close to x equals -4, where am I actually at on the function, okay? So it says as I'm walking along this function and I get really close to -4, where am I actually at? Well, I'm almost to y equals 1, right? I'm almost there. If I get really, really, really close to -4, I'm almost to y equals 1. Now this one, I'm going to look at the other way too, and I say if my friend is walking this way, and we are getting really, 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 really close to -4, I'm also approaching -1, okay? So for this one, the function as x approaches -4, the limit, did I say the function? The limit as x approaches -4 of f of x is 1. Because as I get close to -4, I'm also getting close to -1. Now, if you look right over here, this question says, well, what is f of -4? And we know this from, Algebra 2, that just means I take this value right here, I plug it into my function, and I see what I get out, right? Okay, well, let's look. Here's -4. Well, I look here, f of -4, if I put a -4 into my function, I'm also going to come out with +1 as my output. So f of -4 is 1. That's kind of convenient, right? That the limit and the function value are the same. And you'll see that sometimes that's the case and sometimes it's not. So let's look at the limit as x approaches -1. Okay, so again, if I'm walking on my function and I'm walking toward -1, where is my function going to go, right? So I'm getting really close to negative 1, and what am I actually doing? Well, I'm getting really close to the y value of 4, right? So as x approaches negative 1, I get really, really, really close to negative 4, or to positive 4, excuse me. Well, let's look at the function value. If I plug negative 1 into this function, I come over here to negative 1, and then I look, and actually this function is not, see this open hole? It's not defined right there, is it? It's actually defined right here. So f of negative 1 is actually 1, not 4. So in this case, the limit and the function value are not the same. So let's take a look at the limit as x approaches 2 of f of x. Okay, so let's walk along our function and see what happens. Okay, so as I'm getting really, really close to positive 2, what am I doing on my function? Well, I'm getting, as x gets really, really close to positive 2, my y, I'm getting really close to y equals 1. So my limit as x approaches 2 is 1. Now let's a question for f of 2. Okay, so I have f of 2 right here. So if I plug 2 into my function, what am I going to get out? Well, we have a hole right here. And this hole tells me that this function is actually not defined there because there's no other point. There's actually not that point 2 on my function. Okay, so I'm going to say f of 2, it does not exist. DNE. Okay, now let's take a look at the limit as x approaches 3 of f of x. Okay, so this one, if you look at it, here's 3 right here, right? Okay, so we're going to get really, 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 really close to 3. And what's actually happening is that this is a vertical asymptote, and as x gets close to 3, y keeps getting bigger and bigger and bigger in the negative direction. So I guess we could say smaller and smaller. But it just keeps going more and more and more and more negative, right? And it never stops. We know that like it's going to get really, really close to 3. It's not actually going to touch 3, but it's going to become like a hugely negative number. So the limit as x approaches 3 is actually going to be negative infinity, or you could write does not exist, because there isn't actually a limit. It's actually unbounded at this point, which means there's no limit, but a lot of times we'll say that the limit is negative infinity to help us know that it's not a discontinuity like this, it's that it's an asymptote. Okay, so then what is the value of f of 3? Well, again, it's not defined there because it's an asymptote, so this one also does not exist. Okay, so let's look at the limit as x approaches 5. Well, if we go on, let's think about two different people walking on this function, right? So one person is walking on this place, and they're getting really, really close to negative 1. So they're walking on the function, getting really close to 5, and they're almost to negative 1, right? Well, this person is also walking on the function, and they're approaching x equals 5, but they're getting really close to positive 2. In fact, these people were never going to meet, right? If this person keeps walking on this function, and this person keeps walking, and they stop here, right, really, really, really close to x equals 5, they're not anywhere near each other, right? So there actually is not a limit as x approaches 5, so that one is also a does not exist. And now the question is, what is f of 5? Well, if I'm right here on x equals 5, there's a hole here, so it doesn't exist here, but it does actually exist here at y equals 2, so f of 5 equals 2. So when we have something like this, where the function kind of goes one spot and then it jumps, it's called jump discontinuity, but when we have something like this, we can look at the limits from either side, and that's called a one-sided limit. So we don't just have to look at it from both sides. So we can say, well, what is the limit as x approaches 5 from the left or from the negative side? And then we could say, what is the limit as x approaches 5 from the right or from the positive side? So if you look at this one right here, you see that little negative sign right there. So what we're saying for this one is, what is the limit as x approaches 5 from the negative direction? Okay, so here's the negative direction over here, and we're going to approach 5. So we're starting here, and we're going to walk up this function until we get really close to 5. Well, as we get really close to 5, we approach y equals -1. So the limit as x approaches 5 from the negative direction is -1. And then we look at it from the positive direction. That's what this plus sign means next to the 5. That means that we're looking at it from the positive side. So we're going to look at this one again, and we're going to say, okay, if I'm walking along my function from the positive direction, and I'm getting really close to +5, well, I'm approaching the value of 2, the y value of 2. So the limit as x approaches 5 from the positive direction is 2. So this brings up an interesting concept of continuity, which basically is whether or not a function is continuous tells us where we could draw that function without lifting a pencil. Okay, so continuity basically means the function is connected, right? So let's look at this like an informal way of thinking of this. Okay, so if I could start drawing this function, and then it will be continuous as long as I don't have to lift up my pencil, right? So I'm drawing along here, and I still don't have to lift my pencil. So this is still continuous. This is really good. Still continuous, still continuous. And then right here, I can't keep drawing because the function doesn't exist at that point. So I have to jump, right? So at this point, this is all continuous up until this point. Then that's a discontinuity. So I'm going to start on the other side of the discontinuity, and I'm going to come down here. And again, right here, I can't draw a line through that point because it doesn't exist. So there's another discontinuity. And then I keep going, and at this point, I would go forever and ever and ever and ever and ever in the other direction, and that would be another discontinuity. So a vertical asymptote is a discontinuity. And then I'm going to come here, and I can keep this, it's continuous from this, from this point all the way up till here, and then I have to lift my pencil to be able to finish drawing the function. So it's discontinuous at this point as well. And then the interval from 5 to infinity, as far as we can tell, would be continuous. So that's just the intuition behind continuity. The actual definition is that it's continuous where its limit and function value are the same. So let's take a look at that. And basically that means, like right here, where we had x equals, at x equals -4. X equals -4, the function value is -4, and the limit is also -4, which means that as I get really close to -4, I'm approaching the same value that function value is. Okay, so I mean, it makes sense, right? Because if I don't have to lift my pencil up, as I approach that limit, I should be able to go right through the function value and keep going to keep it continuous. So a function is considered continuous when the limit and the function value are equal. And we're talking about the limit from both sides as well, because you can see where we have a discontinuity like this, the limit from each side is not equal, therefore the function is not continuous at that point. Okay, so list the x values of the discontinuities of the function that we graphed above. Okay, so let's see, where are the discontinuities of this function? Well, if we just walk on the function and we have to figure out where I would have to jump, okay? So if I keep walking, I'm totally fine, but at x equals 1, I would have to jump to stay on my function, right? So one of my I'll just write it right here. One of my discontinuities is x equals 1, a negative 1. Okay, and then we'll look at some more discontinuities. We come here, we keep walking down. I'd have to jump at x equals 2. All right, then I'd have to come here. After 2, I would have to, at 3, I could no longer keep going, right? So 3 is a discontinuity. And then if I come over here, at x equals 5, I would have to jump to get onto my function. Okay, so x equals 5. So the discontinuities for this function are at x equals negative 1, 2, 3, and 5. Now, there are different names for these different types of discontinuities. So let's take a look at those really quick and see which ones are which. Well, the first type of discontinuity is a jump discontinuity or a break. And that would be something like this one. Okay, so it's like you're approaching one value and then you jump to a totally different value and then keep going. That's a jump discontinuity. So that's this one. That's a jump. And then we know what this one is called. This is a vertical asymptote. I keep calling it a horizontal asymptote. Anyway, it's a vertical asymptote. So that would be an asymptotic discontinuity. Basically, we would usually just talk about the fact that there was an asymptote there. Okay, and then the third type of continuity is called removable continuity. And basically what that means is if I could fill in that point right there, that would remove the discontinuity. Okay, so I would look at, basically it's just a hole in the graph. Removable discontinuities are mostly defined as a hole, but we would call them, the official term would be a removable discontinuity. So we would look here and see, are there any places where there's a hole in the graph that I could literally just fill in to remove the discontinuity? Well, that would be at x equals negative 1 and x equals 2. These two are removable discontinuities. And then this one at 5 is a jump discontinuity, and then this one is an asymptote. So that's what this says here. All discontinuities can be classified as removable or non-removable. So an asymptote would be a non-removable one, right? Because we can't just like put a point in. So removable discontinuities are holes in the graph, and non-removable discontinuities occur when the limit of the function does not exist. So that would be at a jump or at an asymptote. So which of the discontinuities from example 13 are removable? And we said that was at x equals negative 1 and at x equals, was it 3 or 2? I can't remember. At 2. Okay. So at x equals 2. I got to turn my pen on. There we go. At x equals 2 and x equals negative 1. All right. So let's talk a little bit about direct substitution. Back here we saw that sometimes the limit and the function values are the same, right? So if I plugged in negative 4 into this function, I would find not just the value of the function, but I would also find the limit. So if a graph is continuous, you can just plug in that number for x, and it will give you the limit, which makes total sense, right? If the function is continuous, then it means that you can draw it without ever lifting your pencil. So if I wanted to know what value it's approaching at this point right here, well, it's approaching that point, right? It's just approaching right to that point. So I can just plug the value in at that point and find the limit. So direct substitution is usually the first line of defense when trying to find a limit. You just plug it in. So when it says, what is the limit of this function, you plug in that number and see if it works. Now, if it doesn't work and you get like a 0 in the denominator or a negative under a square root or something else that's illegal, then you start to have to do other things. But basically, just plug in direct substitution first and see what happens. So let's take a look at this one. Well, the limit as x approaches 3 of this function, we're just going to plug 3 in and see what happens. We have 3 times 3 squared plus 2. So we have 27 plus 2 is 29. So the limit as x approaches 3 of this function is 29. Because this function is continuous, this doesn't have any places where it's undefined, so we can literally just plug 3 into this function, and that gives us the limit. So then this one, same thing. We can just, the limit as x approaches 1, we just plug 1 in. 1 squared plus 1 over 1 plus 1 is 2 over 2. So the limit of this function as x approaches 1 is 1. So as x is getting really, really close to 1, we're getting really close to y equals 1. Okay, so let's look at some piecewise functions. In piecewise functions, if you're evaluating the limit at one of these, like near the domain restriction, then you're going to have to do one-sided limits. For example, let's look at this one. We're trying to say the limit as as x approaches 1 of f of x. Well, let's see, because we know that it changes from this function to this function at x equals 1. So we need to see, well, what are each of those functions approaching so that we can tell if there's a discontinuity there or not. Okay, so let's do direct substitution. So we're going to say this first one, we're going to plug 1 in there, and we're going to say 4 minus 1. Well, that equals 3. So we know the limit as x approaches 1 from the negative side of f of x equals 3. Now let's see the limit as x approaches 1 from the positive side of f of x. So we're going to use direct substitution again, and then we're going to go 4 times 1 minus 1 squared. So that's 4 minus 1, that equals 3. So it turns out that as we approach this function from the left side, we're approaching 3, and as we approach this function from the right side, we're also approaching 3. So in this case, this one is a continuous one, and it does have a limit of 3. Let's look at the next one. If g of x is this piecewise function, well, we're looking at the limit as x approaches 1 of this function. So let's see what's happening from the left side, which would be this one. Okay, so 3 times 1 minus 1 cubed. So that would be 3 minus 1, which is 2. So the limit as x approaches 1 from the negative side of g of x equals 2. So then let's find the limit as x approaches 1 from the positive side of g of x. And so we have 2 times 1 squared minus 1, which is 2 minus 1, which is 1. So from the left side we're approaching 2, and from the right side we're approaching 1. That means this limit does not exist, because this is a jump discontinuity. Okay, and so for the same function, we want to find the limit as x approaches negative 1. Okay, well, that, if you look at this, what is the function at x equals negative 1? Well, this function is only valid if x is greater than 1. So when x equals negative 1, we're just using this function completely. You know, this function doesn't even exist yet. It's too far over on the graph. So we don't actually have to evaluate it from the left and the right, because we're just talking about one function in this case, so we'll just try direct substitution, because again, this is a continuous function. This doesn't have anything illegal in it that's going to make it have a hole in the graph. So we're going to look at that and we're going to say, okay, so when x equals -1, we'll say 3 times -1 minus -1 cubed. So that's going to be -3 plus 1, which is going to give us -2. So the limit as x approaches -1 of g of x is -2. And finally, we're going to look at the greatest integer function, also known as the step function. You may or may not have seen this yet. I remember seeing this for the first time possibly in Calc 1 or 2. I just remember someone talked about it as if I should have known what it was, and I didn't. So we're going to take a look at it just to make sure you at least are familiar with the greatest integer function. It's written like this. That's what it looks like, right? It's got these little brackets, but they've only got the bottom little L shape there. So the greatest integer function looks like that. And basically what it means is if I put in any value for x, this function spits out the greatest integer that is less than that x. Okay? So if I put in any value for x, out comes the closest integer that is still less than that number. So let's take a look at that. So if I put in 1/2 for x, well, 1/2 is not an integer. Remember, integers are whole numbers, negative and positive whole numbers, including 0. So if I put in 1/2, the closest integer to 1/2 that is not over 1/2, right? This is like the Price is Right. The closest without going over is 0. Okay? So the greatest integer function, f of 1/2 would be 0. And then the question would be, well, what is f of 1? Okay, well, if I put 1 in there, I need the greatest integer that is not bigger than 1. Well, 1 is equal to itself, so that's fine. So f of 1 for the greatest integer function would be 1. And so on and so forth. So f of -1/2 would be -1, because it's the closest integer to -1/2 that isn't bigger than -1/2. So let's look at this when we're talking about limits. So here we have the limit of 1/2 of the greatest integer function. So again, we're going to say, we really could use direct substitution on this one, because if we look at the graph at 1/2, this graph is not discontinuous. That's a double negative. If this graph is continuous at that point, right? It's continuous. So what does this graph equal at that point? Well, when I plug in 1/2 to this function, it spits out a y value of 0. So by direct substitution, the limit as x approaches 1/2 of the greatest integer function is 0. Now, if I look at this one, the limit as x approaches 1 of the greatest integer function, what would it be? Well, let's think about what's a number that's really, really, really close to 1, but less than 1. So let's evaluate this from the left side and the right side. Yeah, so let's do that. Okay, so the actual limit of this one is it's not going to exist. Okay, so it does not exist. And this is why. If you look at this, if you look at the graph, it's pretty obvious. It's a jump discontinuity. It can't exist, right? Because if I approach 1 from this side and my friend approaches 1 from this side, we're never going to meet. Okay? But we can look at these as one-sided limits. So we can say the limit as x approaches 1 from the negative side of the greatest integer function. Well, this is where we're going to say, well, what is a number that's really, 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 really close to 1 but isn't actually 1? So we're looking at these values that are just barely less than 1. So like 0.95, 0.99, 0.999999999. Okay, so if I'm at that value, that I'm just barely just a little bit smaller than 1, what would my greatest integer function be at that point? Well, 0.99, the closest integer that is not bigger than 0.99 would be 0. So the limit as x approaches 1 from the negative side is 0, because as those values are really, really close to 1 but not quite 1, they're going to output a value of 0. Now the limit as x approaches 1 from the positive side of the greatest integer function, well, what are some numbers that are just a tiny bit bigger than 1, right? Because we're coming from the positive side, so we're looking at 1.1 or 1.05. Well, the closest integer to those values that isn't bigger than 1.1 would be 1. So the limit as x approaches 1 from the positive side of the greatest integer function is actually 1. So I hope that you have a little bit better understanding of limits and how to look at them from the graph and how to intuitively think about them, and then we will keep building on this in the next section.